Swayam Prabha. Digital India. Educated India.
Welcome to another session of blockchain technology and applications. So, last time we talked about the superficial overview of how Hyperledger blockchain works. What we want to do in this session and the next session is to actually take you a little bit inside the theory that is behind the particular design choice that the Hyperledger people made. And if you understand these design choices, you will understand the goal of Hyperledger blockchain or similar enterprise blockchains. So, much of this material is from Fred Schneider and the original Hyperledger fabric paper that is available in archive. So, we have been discussing this several times, but there is no harm in repeating that the first generation of blockchain, which basically means Bitcoin and similar cryptocurrency blockchains like Ripple coin, Dash coin, etc., is basically for storing and transferring of value. They had very limited ability to program the transactions, and that limitation kind of prompted the idea of Ethereum and similar second generation blockchain, which is programmable via smart contracts. We are now seeing is what we call third generation blockchain and or enterprise blockchain. And enterprise blockchain, one of the early forerunners of the enterprise blockchain is Hyperledger, and then we will also see Coda very soon. And then soon there will be other blockchains which are highly scalable with high concurrency. But let us focus now on Hyperledger. But before we focus on the design choices of Hyperledger, let us understand this notion of order execute paradigm. So, most smart contract based blockchains, they actually follow the idea of what is called a state machine replication. So, state machine replication will go more into details of that in this session or in the next session, is the idea that if I want a system to be fault tolerant, then I have to replicate the service. So, let us say I am providing a service, let us say a database service, but I want to make sure that if my service crashes, for example, then I should be able to still serve the customer or serve the users. So, what people have done, and this is more than 40 years old theory from distributed computing literature, is that you make replica of the, so you can think of a service as a state machine, right. So, you start with an initial state, the user interacts with you, you change the state and you then interacts with some more, and then you change to another state and so on and so forth. So, you can think of a program or a service as a state machine. So, if you want to serve customers irrespective of possibility of let us say crash, then what you would like to do is to have a replica of the same service, but that replica must reflect all the state changes of the original machine, because otherwise suppose I crash at some point and then the user request is routed to the replica. If the replica is still in the initial state, then a replica will not be able to serve correctly the customer, and the customer it will be or the user, and the user will be will understand that I am not anymore talking to the service I was talking to. So, in order to make it transparent to the user as well as give availability to the service, you have to have the replica always be in lockstep with the original services state transitions. So, therefore, you have to replicate what is called a state machine, and this is the idea of state machine replication. Now, as we will see that other than crash, there are other possibilities. For example, a particular service may be down for maintenance. So, in that case it is not really a crash, it is actually a known declared downtime for one of the component of the service. Another possibility is that either the original or the backup replica will actually start behaving weirdly, because it has been taken over by a rogue entity, or it has been affected by malware, or somehow its program starts behaving strange. And in such case, we say that that is a Byzantine fault. So, there are all these different kinds of fault models people thought about when they started talking about this replicating services. And we will see that that is where the original problem of consensus came into existence. Then you have to be in a consensus, so that you are all agreeing on the next state, for example. Now, in case there is a fault, then also you have to keep maintaining this state transition as you interact with the user. So, this is called the active replication. So, a protocol for consensus or atomic broadcast needs to order the transactions that propagate to all the peers. So, transactions may come to your system, and you have, let us say, replicas, 4 replicas or 2 replicas, whatever, for your service. Now, depending on where in the network these replicas are, the transactions may come to the primary replica, or it may come to one of the secondary replicas. Now, as we saw before, that if I give money from A to B, and then B tries to give money to C, then if B's original balance was 0, and the B to C transaction is only possible when A gave some money to B, then that ordering is very important. If the ordering is done differently, then in one case both the transactions will succeed. In the other case, if B to C goes first, then it will not succeed, but A to B will succeed. So, as a result, if different replicas do the transactions in different orders, then you will see the replicas are now out of step, their states will differ. In order to avoid that, what you have to do is you have to ensure that the transactions are ordered and everybody agrees on that ordering. And if that ordering is agreed upon, then the state will also go in lockstep. So, in Ethereum, for example, what happens is the consensus step decides that ordering, right. Remember that all of the miners are trying to create a block, and in that block they choose the order of the transactions, and then everybody else, once the block has been actually created through proof of work or whatever the process is, then it is being sent to every other node, and every node will eventually agree to add that as their blockchain next block, and therefore, the state will always be the same. But one of the major issue is that ordering will never be different in different nodes, because the ordering is done by the winning or the mining node. So, consensus is done first in Bitcoin, in Ethereum, and then once the consensus is done, then every other node falls in their in line with the same ordering. So, therefore, we call it an order execute paradigm, which means that ordering is first and then execution. Execution means that every node will change their state in the same way, right. And then when the block goes to the other nodes, they will then do the transactions. They also have to remember, they have to also run the same transactions and change the states and so on and so forth. So, they have to do this sequentially as they get the block that wins. So, this order execute architecture has been the first 2 generations of blockchain, has been characterized by this order execute paradigm, and it requires all peers to execute the transactions, and all transactions have to be deterministic. Remember that in Ethereum we cannot have a random call to a random number generator, for example, because we do not want non-determinism, because once the block has been decided, order has been decided, then that block goes to somebody else, they will also execute all the transactions, and if there is non-deterministic execution, then the state in one node will be different from the state in the other node. So, determinism is a must. So, order execute architecture is in Ethereum or in some other permission based ones like Tendermint, Chain and Quorum, and then transactions must be deterministic. So, these are the hallmarks of the earlier generation of blockchains. The second issue is that, remember, in Bitcoin you cannot overnight change the consensus mechanism, then you have to do some kind of a hard fork, right. Similarly, in Ethereum you cannot change the consensus mechanism, you have to do a hard fork. So, therefore, the transaction, we say that the consensus mechanism in these blockchains are hard coded, you cannot change them and without creating forks. In a Hyperledger and more recent blockchain, they have somehow extracted out the consensus mechanism, so that you can actually, depending on your need, you can change the consensus mechanism. So, the trust model of transaction validation is determined by the consensus protocol. So, trust model means what? Like, so in case of Bitcoin you do not trust any of the other nodes. In case of Ethereum also, you assume that nobody is trusted, and even the smart contracts are coming from anybody and everybody, they can actually deploy a smart contract. So, the smart contract itself may not be actually honest, and therefore, the trust model is that do not trust anybody. But in a permission blockchain, since you have strong identity of each node or each user, therefore, you can decide what will your trust model be. For example, as I was saying, that if your blockchain has multiple organizations participating, then all the SBI, let us say SBI, UBI, they are all together doing maintaining a blockchain and doing all their transactions on the blockchain. Then you can assume that the SBI employees, they know each other because their identities are clear, and UBI employees know each other, their identities are clear. So, they can trust each other, but trust within their group, but may not trust across the group. So, this is one type of trust model. Another type of trust model could be that you do not trust anybody. So, you do not even trust your SBI colleagues, you do not trust your UBI colleagues, and then your mechanism for transaction validity, etc., will be lot more complex, because then now you cannot trust anybody. But if you can trust somebody, then your mechanism for transaction, whether the transaction is valid or not, etc., will be different. So, now this trust model is different from the consensus trust model. The consensus trust model is about what is the fault, what is the fault model you are assuming about the consensus mechanism. So, remember, the consensus mechanism is about ordering the transactions, and so if you assume that the nodes that are participating in the consensus mechanism, some of them can be rogue or some of them could be affected by, let us say, malware, then you have to have a very strong consensus mechanism. If you trust all these nodes, then you can have a very simple consensus mechanism. So, therefore, what you have to do is that you have to consider two different trust models. One trust model is about those who are doing transaction among themselves, how much they trust each other, and another trust model is that those nodes which are autonomous and which are doing the consensus, how much you can trust those. And in Bitcoin and Ethereum, these two trust models are intermingled. There is no difference in these two trust models, but in a permission scenario, this can be very different, and therefore, we have to somehow extricate the one from the other and have two different trust models, and you can play with the trust model. You may have, if you have a very nice secure set of nodes which are doing consensus, then you can fully trust that, whereas since the transactions are coming from outside, from clients and so on, you may not trust, or you may see that all the people who are doing transaction are within your organization, you trust them, you can have a good trust, but you may say my consensus mechanism is maybe faulty, some nodes may actually crash and so on. So, I cannot trust that fully, so I have to have the right complex consensus mechanism. So, you can have all kinds of mixes of the two trust models. So, other thing is that in Bitcoin, for example, you have to write any kind of complex logic, business logic, like micropayments or escrow, etc., in a non-standard fixed language called Bitcoin script language. In the case of Ethereum, you have to write them in Solidity. Now, there are some few other languages which can also convert it to the EVM bytecode. But in case of Hyperledger, as I said before, you can write the smart contracts in any programming language, because there is no EVM concept or VM concept associated with them. You are basically going to execute the smart contracts inside Dockers and in a regular programming environment. And this fixation with specific language is hindering the wide adoption of this blockchain technology, because there are not many people who knew Solidity, not many people who knew Go, but lots and lots of people know Java, C++, Python, etc. So, you can do that. Now, another issue is that in Bitcoin and Ethereum, etc., once you get a block, you have to execute all the transactions in that block, even though you did not mine that block. And so, therefore, if a transaction, if a smart contract that you are executing is very time consuming, then you might get into an infinite loop or very long loop, and then that particular node will become engaged for a long time, and that can lead to what is called a denial of service attack. That node will not be able to add to the blockchain, and therefore nodes will be busy processing the last block's transactions. So, in Ethereum, this is solved by using gas mechanism, right. But in the gas mechanism works because Ethereum has a native cryptocurrency. So, you can talk about WOI, that is the smallest unit of Ethereum, and you can say gas costs so many weights and so on and so forth, and you can do that. But if you are having a permission blockchain in a private setting, you do not have a native cryptocurrency, therefore, you cannot really have this notion of gas or incentive mechanism like in Bitcoin, and therefore, you cannot stop this possibilities of infinite loop and so on. And so therefore, this you cannot afford to run the smart contracts at every node. Smart contracts are only run on specific nodes which you trust, and the smart contracts are written by specific entities that you trust. So, therefore, you assume that they will not put in an infinite loop or some kind of a very computationally intensive logic inside the smart contract. So, because you are trusting so much, you can afford to do that. Therefore, that is why you are writing programs in general purpose language C, C++, with which you can do such things like creating infinite loops very easily, but you assume that smart contracts are not written by random untrusted people. It is written for specific business purpose by the entities that you know very well. Their signature is associated with the smart contract, and corresponding to their signature there is a digital identity and so on. So, therefore, you can afford to do that. Also, in those platforms like Ethereum, therefore, remember that otherwise there will be divergence if the smart contracts have non-deterministic logic, because once the block comes to you being mined by one of the nodes, you have to execute the transaction. If the transaction was non-deterministic, the result you will get will be different from the other blocks, what the other nodes will get, and then there will be a fork in the blockchain, and this will be too often, and therefore, you cannot afford that. So, determinism has to be inbuilt into the language in which smart contract is written, and to do that your language should be designed, and that is why there is specific languages like Solidity or Ethereum scripting language, which do not have any construct for non-determinism. And then again, this we talked about earlier, that every smart contract runs on every node in case of Ethereum, which means that every node needs to know your smart contract, the bytecode of your smart contract. And therefore, any intellectual property you have in the logic of the smart contract, or any business secret as to how you process transactions, how you make decisions on the transactions, etc., will be known to everybody else. That is also not desirable, and therefore, the confidentiality of the business secrets, etc., is not kept, and therefore, we need to have some way of also not having a system in which smart contracts will be run at every node. So, all these things that they figured out in the earlier blockchains that they want to make a difference from. So, Hyperledger has many different incarnations. So, Hyperledger Fabric is the one of the most used one. So, we are talking about Hyperledger Fabric. There are other implementations of Hyperledger, but Fabric is the, I would say, most canonical implementation of Hyperledger, which is done by IBM. So, Fabric is the first blockchain system so to support execution of distributed applications written in any programming language. So, this gives us the ability to attract people to use it. So, there is adaptability will increase, because if I have to code a business logic in C, I already know C, I do not have to learn Go or Solidity or whatever. That makes the barrier to entry into this technology much lower. So, the architecture of Fabric follows execute, order, validate. So, earlier we were talking about order, execute. So, order first, execute next. Now, we are talking about execute, order, validate paradigm, and we will explain what that means for distributed execution of untrusted code in an untrusted environment. So, it has a transaction flow which has 3 steps. First, executing a transaction and checking its correctness and thereby endorsing it. So, there is a step called endorsement. So, when client or the user of the application proposes a transaction, for example, give this much money from my account to somebody else's account, or give this much price for the entity I am purchasing from that other entity, then the endorsers are certain nodes which will simulate the execution of that transaction and say, if the transaction happens, then this will be the final situation. Your account will be debited, that account will be credited, or things like that. So, that information along with an endorsement which comes in the form of a digital signature of the endorser comes back to the client or to the code that is running on behalf of the client. Then after, and this endorsement may be from one node or it may be from multiple nodes, depending on what is called an endorsement policy. The endorsement policy is also flexible. So, then once you got enough endorsements as per your endorsement policy, if the endorsement policy says one endorsement is enough, that is fine, that then you are done with one endorsement. If it says that it has to be 2 out of these 3 nodes, then that also has to be gotten, things like that. And then what you will do is that you send this endorsements with the possible changes in the state, that is how much your balance will be, what will be deducted from your balance, what will be added to the other balance, etc., to the ordering service. Ordering service will then order the transaction. Ordering service does not care about the semantics of the transaction, it does not execute the transaction, it just do the check the read write sets and order them. And there is some notion of a version issue also, but right now let us not worry about it. just want understand this, that transactions will be ordered and a block will be cut, and that block will be sent to peers called validating peers. So, then validation will be done by these validating peers. What they will do is they will check which transaction is meaningful, which transaction is meaningless, and they will mark those transactions which are meaningless, and for the rest of the transactions it will use the read write set to change the state replica of the entire system in its local copy and add that block to the end of the blockchain. So, this is validating peers are also designated peers. Not everybody in the network has to do validation. So, you see that for a transaction, not everybody executes the transaction, or everybody does not need to endorse the transaction. For each transaction or application, there is a transaction endorsement policy, and that has to be fulfilled. Similarly, validation also is done by specific validating nodes, and when we come back we will get into more details of Hyperledger Fabric.